first speaker of today is Wolfgang Schief from the University of New South Wales, and he'll be talking about discrete analogues of some very classical and beautiful geometric objects. So without further ado, I'll give the floor to Wolfgang.
Yeah, thank you, Peter. All right, so well, as always, it's a great pleasure attending Alini's workshop series. So it's a long title as usual, and you might think, well, is Wolfgang attending the right conference here? So what's the connection with integrable systems? So really this is to do with sort of the general question, to what extent we can push this analogy between classical differential geometry and discrete differential geometry. And as you know, differential geometry and discrete differential geometry are quite important in integrable systems theory. And so you probably think that the more intricate the properties are of some geometric objects, the harder it gets to find discrete analogues of them. And that's probably generally true. And so I'm going to talk about some sort of rather probably obscure theorem. I'm very much inclined to quote Sir Michael Caine. Yeah, not many people know that. So, and actually I didn't know it myself when I first saw it, or someone told me about it. So this is really something that started a number of years ago, and I never got around to actually follow it through. And then I had an honors student 2 years ago, Boris Huang. And I said to him, okay, so you look at it. And he came up with some very interesting results. And then we're just about to write up the paper. And then I thought, well, you know, my colleague in Germany, Jan Techter, this would be exactly right up his street. And so I got him involved, and he already made some really, really nice contributions. So hopefully that paper will be published, you know, in the not too distant future. Okay, so now the usual problem here is that you really have to explain the sort of classical contexts first, so that people know what you're actually trying to discretize. Now that's, so it will take some time to do the setup, and then I'm not quite sure how much time I will have actually to explain the discrete case. But as usual, it really is, in this business, it's a matter of finding the right formulation of the classical geometry in order to be able to discretize things. And usually if you find the right formulation, and there are different ways of putting things, once you've found the right formulation, it's almost a one-to-one translation into the discrete setting. And so in fact, really spending some time on developing the continuous case, the classical case, is really most crucial in this business, and I think it's also important in the talk. Anyway, so let me start with a few pictures, and I will try to keep the number of equations down, because I think maybe pictures are probably better to explain things. So here you can see something that is taken from a classic, which is Hilbert and Cohn-Vossen, Anschauliche Geometrie. So this is the English translation, 1952. And so this is actually a model of an ellipsoid. And it's just cardboard discs attached to each other in such a way that you can actually deform this ellipsoid. So if you deform this, so wherever they, you know, those cardboards meet, so that they're basically slits, and so you can move those cardboard, then you deform it, and they end up with something like this, which I think is not a proper, I think this is distorted. But anyway, these are exactly the same cardboard discs, but you see the shape changes, and but it's still a model of an ellipsoid, right? And so there's also some wire models here. For instance, if you go to the Institute of Discrete Mathematics and Geometry at the Technical University in Vienna, they have a collection of models, and you can find those. So this is a wire model, and so you have just circular wires, and they are, wherever they touch, they are attached. And so this is deformable, and you can see you even get a sphere if you deform it. Well, if you deform it sufficiently enough. And in fact, this was already pointed out by Hilbert and Cohn-Vossen in their book, that if you deform it at some stage, you actually get a sphere. All right. So what's the actual theorem? So here's the theorem. And there are two parts to it. So the first thing which I found amazing when I first learned about it, I mean, if you have an ellipsoid and you take a slice with a plane, of course you get an ellipse, right? So you get a conic section. But if you do it in a certain manner, you actually get a circle. And in fact, there are two one-parameter families of circles if you cut the ellipsoid appropriately. And so how do you do this? Well, there are four special points. If you have a non-spherical ellipsoid, there's four special points on that ellipsoid. So you can see two here and then there are two down here. And these are called umbilical points or umbilic points. I will explain what they are in a second. And then, for instance, take this one here. You take a tangent plane to that to the ellipsoid at this point, and you then just take all the parallel planes to that tangent plane, and then you get a one-parameter family of circles. And then you take the other one here, play the same game, and you get another family of circles. So you have these two one-parameter families of parallel planes, and they are parallel to the tangent planes at the umbilic points. So the tangent plane here, this umbilic point, of course, is parallel to the tangent plane by symmetry at this point. Okay, so that's the first part here. So what's an umbilic point for those who don't know what this is? So really, you don't really have to know a lot of geometry here, or even integrable. I will point out some connections with integrable systems, but this is going to be fairly recreational here. So let's take this ellipsoid here, and you take a point on this ellipsoid. And the blue lines that you see here are lines of curvature. So if you go in this direction along this line of curvature, then you have maximum change of the normal curvature. Here you have minimum change of the normal curvature. And those directions of minimum and maximum curvature, they are orthogonal to each other. So there's a right angle here, right? Now, and this generically happens if you have a surface. You always have well-defined lines of curvature, maximum normal curvature, minimum normal curvature. But there are points where the curvature is the same normal curvature regardless of in which direction you go. And these are exactly those points are exactly the umbilic points. So if you look at this very closely, you can see something is happening here, and basically the coordinate system breaks down. And so here, it doesn't matter in which direction you go, the normal curvature is the same. So there are really four special points on those non-spherical ellipsoids. So if you have a sphere, then all points are umbilic points. Okay, so now the claim, so that's number one. The claim is you can now deform this here, this ellipsoid, in such a manner that the circles actually don't change. They just change their relative position. And then you get something like this. In fact, there are three extreme cases, if you like, or two extreme cases and one in the middle. So this is the spherical case. So just start with, let's say, this one here. This is the previous picture, and then you start deforming. Now, if you deform it in two directions, so the last state you get in this deformation is a planar figure, and you have exactly the same yellow circles. So they don't change. They're just sort of rotated and translated. And then at some stage you get a sphere. And then if you continue, again, you get a planar state. All right. So you have this sort of observation that, the deformation goes from a flat configuration to a spherical configuration and back to a flat configuration. And because of the symmetry, you can see that, in fact, one semi-axis of the ellipsoid doesn't change in that deformation. So it's exactly this semi-axis here that remains the same. And that's a crucial observation. But basically, you're just those yellow circles here, they are rotated about this semi-axis, this axis here, and sort of translated orthogonally to that. Okay, so that's why the semi-axis doesn't change in the deformation. Okay, now if you have any questions, just interrupt me. So I might, because I'm looking at my iPad, so I might not see questions popping up. All right, so.
May I interrupt you with one question?
Yes, yes, sure.
Now, regarding those deformations, I'm So you rotate the circles around that fixed axis of the ellipsoid in the deformations. And I'm wondering, these confocal nets that we see on those ellipsoids, how are they deformed in these transformations?
I will answer that question. That's exactly the point. So you put your finger on it. So just be patient. So that's an excellent question. Yeah, that's exactly the point. Okay, so in fact, I will talk quite a bit about confocal coordinate systems. Yeah. Now what you see here, if you look at this very carefully, you can see I've done something that is absolutely non-trivial. I've taken a sample of those lines of curvature, and I have taken a sample of those circles. And you can see that those circles and those lines of curvature always meet in a point here. So you can think of those circles as being the diagonals, if you like, of those, that piece here, so the circular diagonal of this curved quadrilateral. And it's absolutely non-trivial that this is actually possible, that I can actually find the sample of those lines, nets, that this is possible. So as a matter of fact, there's something very special. And so this is, now I have to explain to you what diagonally related nets are. So you have two nets, and so think about the net N1 as the lines of curvature. But this is what I'm saying here, the definition is general. So this would be the lines of curvature, then I have another net N2, which is, let's say, the circles. And then there's a notion of those two nets being diagonal. And so what the problem here is, so let's say I draw 3 lines of curvature, so 3 lines of this net, so those 3 lines, okay? Now when I do this, then I can take, for instance, this point of intersection, and I can draw a unique curve of that second net, say, let's say there's a circle, which is going to intersect my line of curvature here. Now then there's a unique line of curvature going through this point, which is this one here. But then there's no reason to believe that there is a circle which passes through this point and that point, right? So you say that two nets N1 and N2 are diagonally related or mutually diagonal because it's a symmetric definition. If you have a quadrilateral made of curves of the first net, then if you have a curve of the second net which passes through opposite edges, then there is another curve of the second net which passes through the other two opposite vertices, right? So there's something very, very special about this relationship between lines of curvature and those circles. Now, I don't know whether this is actually a known theorem, but so we published a paper related to, well, it was a more general topic, and this is where we published it, so in that paper here. So cross-sections of ellipsoids and lines of curvature are mutually diagonal. Now, what that means is, if you think about it, it means that if you, if you think about this as the parameter space rather than the curves on the surface, it just means that really in the parameter space, you can find a parameterization such that you just get a square grid with the diagonals. So in other words, this means that you can find a parameterization of an ellipsoid. So U and V are curvature coordinates, such that the lines U equals constant and V equals constants are the lines of curvature. And then if you just U plus or minus V, you get the circles. Right, so that is an extremely nice property. And you can see why this is useful, because now at some stage we want to discretize this property. Well, if U and V are integers, then so are U plus minus V. Right, so you can see, so somehow there might be a notion of discrete diagonally related nets. Okay, and so really the point here is I just want to find an integrable discretization, well, integrable in some sense, a discretization of this privileged and natural discretization of those those nets on ellipsoids, and thereby discretizing ellipsoids. And in fact, there are actually other nice properties, classical properties, which are preserved by that discretization. All right, so how are we going to do this? Well, now I have to talk about confocal quadrics, and I hope that I'm going to answer your question, Milena, that you just asked. So I have to talk a little bit about confocal quadrics. So this is going to be a crash course on confocal quadrics, but again, it's not really very, very deep. So what are confocal quadrics? Well, you take three numbers, A, B, and C, and let's say, without loss of generality, A is greater than B and B is greater than C. And then you can write down a family of quadrics, right? So for lambda, the parameter here, so for each fixed parameter lambda, we get a quadric. But of course, the size of lambda determines whether lambda plus A is well, lambda plus A is always going to be positive, but lambda plus B could be negative and lambda plus C could be negative. So you actually have three different types of quadrics depending on how large lambda is. So if the lambda is between minus A and minus B, then we call it U1. If the lambda is between minus B and minus C, we call it U2. And if the lambda is greater than minus C, we call it U3. And then, so for instance, in this case here, those numbers are always positive, so you get an ellipsoid. In this case, this number is negative, and those two are positive, so you get a one-sheeted hyperboloid. And here you have two negative quantities, so you get a two-sheeted hyperboloid. So you've got so basically a one-parameter family of confocal quadrics actually consists of three one-parameter families of quadrics which have different signature. So here's a picture. So here is, as you can see, we have an ellipsoid here. Then we have a one-sheeted hyperboloid. Here we have a two-sheeted hyperboloid. And there are lots of nice properties of those confocal quadrics. So if you take a point in space, then there are three unique quadrics, confocal quadrics passing through this point, and one of each of those three families, right? And also those surfaces, those quadrics, they actually meet orthogonally. So that means that those lines of intersection of those quadrics, they actually are the coordinate lines of an orthogonal coordinate system. So you can use U1 and U2 and U3 as the parameters of your coordinate system. So that gives you an orthogonal coordinate system. So if you take those three quadrics here and you solve for the squares of x, y, and z, so you have three equations for three quantities, you're going to end up with this relationship here, those relationships here, and that is your orthogonal coordinate system. So of course you have a choice here. You can choose plus or minus, plus or minus, plus or minus here. So you get 8 choices, and those 8 choices correspond to the 8 octants of R3. So for each choice of the signs here, you get a well-defined coordinate system, orthogonal coordinate system in the corresponding octant. All right, so now since we have an orthogonal coordinate system, then, well, that's a classical theorem. I think it's due to Bonnet. Those lines of, so those coordinate lines are actually lines of curvature on the quadrics. So this would be a line of curvature on the ellipsoid. Okay, so you can see the connection already with our lines of curvature that I talked about some time ago. Okay, so what are the integrability connections? Because you were wondering, what are the integrability connections? Well, number one, of course, you may know that orthogonal coordinate systems are governed by a system of equations, differential equations, which is called the Lamé system, and that's an integrable system. So that's classical. Even the integrability is classical. And there's, of course, a standard integrable discretization of orthogonal coordinate systems. But the trouble is that doesn't, that discretization just doesn't do the trick. And this is why it took so long actually to solve this problem. This is something that we encountered when we actually tried to discretize confocal quadrics. It just doesn't work. Now, alternatively, you could think of quadrics, of course, as isothermic surfaces. Now, which are classical, and so there's this pioneering work by Bobenko and Pinkal. This is really one of those two papers that started sort of integrable discrete differential geometry. And so their discretization has become really standard by now, but it doesn't work either in that particular context. So we really have to come up with some new notion of a discrete orthogonal coordinate system. I'll mention this. And sort of the history of this is the following. If you look at x, y, and z here as functions of u1, u2, and u3, then you will see they actually satisfy those quantities x, y, and z. They satisfy a system of linear differential equations, non-autonomous equations. And these are called the Euler-Poisson-Darboux equations. And they're multidimensional consistent. So it doesn't matter whether you have, we have only 3 u's, so u1, u2, u3, but they're actually multidimensional consistent, so in any dimension. So that's the first integrability connection. And in fact, Boris Konopatchenko and I, we discretized that system, preserving integrability, and in a completely different context. So this was to do with discretization of systems of hydrodynamic type and hyperelliptic integrals. And so this is really behind our original work of discrete confocal quadratics. It was really, it started off algebraically. So this is the paper here. But then we realized actually there's geometry behind it. So one has a non-standard discretization of orthogonal coordinate systems. And in fact, so you can find in a purely geometric construction of these discrete confocal quadratics. By the way, what time did I start? Just to
about 3 minutes past 9.
Okay, so I've got about 20 minutes. Okay, 19. Okay, good. Right. Okay, so now remember, we want to find a particular parameterization of the lines of curvature. So we have to get away from this very particular orthogonal parameterization of our confocal coordinates, of confocal quadratics. So of course, what you can do is you can just reparameterize the coordinate lines and you still have lines of curvature, right? And so let's have a look at the structure of those components x, y, and z. So you can see they're factorized. So a function of u1 times a function of u2 times a function of 3. But those functions are not independent. You can see this one and this one, they depend linearly, right? There's a linear relationship between those. So basically, this is captured by by these formulae. So you can have a general parameterization. So here's the claim. So you have this these functions, fi, gi, hi, as you can see. They only depend on one single quantity. And so x, y, and z are the coordinates in R3. And the claim is that if those functions are related by these functional relations, then this is a confocal coordinate system. But it's just a reparameterization of the ui's. And so these are basically the linear relationships for the squares. So any solution of this system gives you a confocal coordinate system. You just plug it in here, parameterized, well, depending on the solution. So let me just give you 2 examples here. So for instance, if you choose the fi's, the gi's, and h's to be just linear functions, or squares, I should say, linear functions, then you can satisfy those relationships. And then we are back to exactly this case here. Right? So that's one parameterization. There's another one which is very canonical, and that's if you look at those relationships. So see, you have 3 functions, f1, g1, and h1, and you're trying to find a solution of those 3 algebraic quadratic relationships. Now, if you only have one, then you could choose, let's say, cosine and sine here. But if you have 2 quadratic relationships, how do you parameterize those 2 relationships simultaneously? Well, you use Jacobi elliptic functions. The same here. So in fact, you can, the f's, the g's, and the h's, you can find expressions in terms of Jacobi elliptic functions which satisfies those relationships. And in fact, what you see here is really a real version of a classic formula that was given by Jacobi, I think. I think this is actually, I believe this is the original context in which Jacobi came up with his elliptic functions. I think. And so if you then try to discretize, those things, then those the square roots that we see here, if we take the square root, they actually become gamma functions, while the elliptic functions, Jacobi elliptic functions, they actually remain Jacobi elliptic functions, and in the discrete case, and in fact, there are connections with the QRT maps. I can't get into that. So I hope that John Roberts is listening. So John will be pleased. So there's actually a QRT connection. Can't get into that. All right. So this is really the setup. So you can see I've spent quite a bit of time on setting it up. So now the question is, how do we relate all this to the problem at hand? So the first thing is that let me remind you that I told you that when you deform this ellipsoid, then the one semi-axis doesn't change. So it makes sense to look at this, to look at the one parameter family of confocal ellipsoids. So if you run through U3, then you get those confocal ellipsoids, but then you normalize them. So you get a semi-axis, let's make it 1 here. So I have just scaled every single ellipsoid in a one parameter family of confocal ellipsoids such that the semi-axis is 1. Okay? And so then if you reparameterize again, then you get essentially the same formula, except there's then a G3 missing, as you can see. And the functional relationships are, those are the same, but since there's only an F3 and H3, what's called F3 hat and H3 hat, now there's only one functional relationship. So that is the idea. So I think, well, there's a natural one parameter family of confocal ellipsoids. Maybe they have something to do with the deformation. But of course, I need to keep this one semi-axis fixed. So maybe I just scale them, and let's see what happens. All right. So now I have to find the appropriate solution of those equations here, which correspond to this mutually diagonal coordinate system, or these mutually diagonal nets. So now, since we know how those mutually diagonal nets are defined geometrically, you can just work it out. And so here's the claim. So if you take, if you look at those formulae here, so you can see it seems to be natural to, take F1 as the sine of something, and H1 is the cosine. Of course, you have to pay a price because then this is not, you get a square root here. So we just parameterize these in the natural manner. So as you can see, sine, cosine, and this is identically satisfied. F2 cosine, H2 sine, then this is identically satisfied. Then you pay a price because then you have to solve for the squares, and you get, well, you know what the squares are of G1 and G2. But of course, in order to find G1 and G2, you have to take the square root. And so basically there are two choices here because only the product of G1 and G2 appear in the in that formula for confocal quadrics. And so you have to make two choices. And in fact, those two choices correspond to the two halves of the ellipsoid that one is actually parameterizing here. So the signs here give you the two halves because each choice of the signs gives you only half an ellipsoid, and then you just glue them together. And also note, of course, at some stage, this here becomes negative, and this is where the coordinate system then stops. And at some stage, this becomes negative, so you can't find a real solution. So there is, so basically what you have here is the pre-image of a half an ellipsoid is actually sort of a rectangular domain. All right, and so the circles now, the circular cross sections are just given by taking S1 plus minus S2 equals constant. Right, so S1 and S2 parameterize the curvature lines, and S1 plus minus S2 parameterize the circles. So that's the nice mutual related coordinate system, diagonally related coordinate system. Okay, so far so good. So now the question is, well, what's the relationship between the circular cross sections on a given ellipsoid for some fixed S3? And then when you change S3, you get a new set of circular cross sections. What's the relationship? Well, it turns out they don't change, except they just change their relative position. So this one parameter family of scaled confocal ellipsoids is exactly the one parameter family that you get by deforming one ellipsoid and preserving the circular cross sections. So Milena, I think that probably answers your questions, doesn't it?
Yeah, I think so. Thank you.
Okay, good. Right. So now you can see we have reformulated the problem in terms of a confocal coordinate system, okay, a scaled confocal coordinate system. And now it's easy, quote unquote. Since we know how to discretize confocal coordinate systems, so this is this work, you know, that I cited earlier, well, we just have to translate this into the discrete language and see what happens, whether we get similar properties. So now, what does translation mean? Okay, now I'm going to give you an algebraic version. So let me just remind you of those formulae. So basically this captures everything here. So I'm going to show you some formulae which look exactly the same, except that now those variables n1, n2, and n3 are discrete variables, and they can take integer and half integer values. And those squares here that you can see here, they are not really squares, they are sort of discrete squares. So you can see they are products of the function evaluated at neighboring points n and n plus a half. So naively, all you do is you replace squares by these discrete squares. So since the n's can take integer and half integer values, when it's actually looking at what you could think of as a body-centered cubic lattice. So you look at the vertices of a cubic lattice and the vertices and the centers of the elementary cubes. So you can think of the dual of Z3 as just Z plus a half cube, right? So you have the union of a cubic lattice and another cubic lattice, and the second one is dual to the first one, right? So this will become important. All right. Now, as I said, you could think, well, that's just a naive discretization, but that's actually not where it came from. So as a matter of fact, the origin of this is geometric. And this is just a result of the geometric construction, which is quite amazing. So what are the geometric properties? Well, as I said, we have sort of the union of two lattices, Z3 of Z3 type and another Z3, but that's the dual lattice. And it turns out that if you look at an edge of the Z3 lattice and an edge of the dual lattice, then they are corresponding edge, they are orthogonal. So dual edges are orthogonal. Which means, if you think about it, and I'll explain this in a minute, that the quadrilaterals of this lattice, the Z3 lattice, and the quadrilaterals of the dual lattice are actually planar. And that is our discretization of orthogonal coordinate systems. So we call this, or I call this dual orthogonality, but this is actually the non-standard discretization of a orthogonal coordinate system. So maybe I remind you, some people know this probably, the standard integrable discretization of an orthogonal coordinate system is a Z3 lattice with all the quadrilaterals being inscribed in circles. So that's something that has been used many, many times in discrete differential geometry, producing lots of integrable discretizations of geometry and differential equations. Okay, so let me just show you a picture, then you can see what's going on here. So here is sort of a Z2 slice, the blue one here, of a lattice. And then you can see this here. So the red edges are edges of the dual lattice. So half integer, if you like. And each edge here, this one here, for instance, is orthogonal to this edge here. This edge is orthogonal to this edge. And this edge, for instance, here, is orthogonal to all the other dual edges. So this one, this one, this one, and this one, which means that, of course, this quadrilateral is planar, right? So all those quadrilaterals that you see are planar. So we have a polyhedral surface, as you can see here, composed of planar quadrilaterals. And another one here. And then, of course, also in this direction here. So this is three-dimensional. And all the dual edges are orthogonal. And so this is our definition of a discrete version of orthogonal coordinate system or coordinate lines. Okay, so here are two pictures. So this is the continuous case, and this is a discrete version of it. Okay, so there's some subtleties involved. I'm not going to get into this because I'm running out of time. So you can see how good a discretization this is. I mean, it really looks the same. So what about umbilic points? So here's an umbilic point. And then if you look at the discrete version of this discrete ellipsoid, you can see something here. There's a point here. Now you wonder what that point is. Well, actually, you think, well, this here is not a quadrilateral, so you're cheating. Well, it is a quadrilateral. There just happens to be two edges which are aligned. There's actually a vertex here. So this is a quadrilateral. But you can see the valence here is 2. So there's only 2 edges connected to this vertex, whereas generically there are 4 edges. So a natural definition of discrete umbilics is vertices of valence 2. And you have 4 of those, 1, 2, 3, 4. So in some sense, we have discretized umbilics here. So let me move on. So now you would have to find a discrete variant of this parametrization that I showed you earlier, which leads to this parametrization, which gives you those mutually diagonally related nets. And well, and you have to satisfy this system here, of course. And I'll just give you the result because I'm running out of time, and of course I can't explain this. But again, basically the algebraic form is exactly the same. So now you have again sine, cosine, but now you have a discrete variable. And let me just point out a few important things. Number one, that delta here is a constant, which is sort of the lattice parameter, which is arbitrary. However, we want to mimic what is happening in the continuous case. So remember, in the continuous case, we had the G1 and G2, only the squares were given. And then you had to calculate the square root. Now, in the discrete case, you have a recurrence relation. We have recurrence relations for G1 and G2. And what we want to happen is that the G1 vanishes at some stage, and the G2 should also vanish some stage, as in the continuous case. And so the parameter domain here is, again, a rectangle for each half discrete ellipsoid. And at the endpoints, those functions should vanish. And you can only do this if you choose your spacing, the lattice parameter delta, appropriately. So that delta actually depends on the choice of N1 and N2. So you can see if you increase the number of N1 and N2, the number of points, then delta becomes smaller, which is exactly what we want. All right. So I think that's basically it. So I'm going to show you some pictures. So what you do is, first of all, of course, we're interested in a one parameter family of discrete ellipsoids. So we still have this discrete parameter N3. So we just let this go to we just introduce a semi discrete limit so that we have a one-parameter family of discrete ellipsoids. And then what we then do is we take those we have this domain and the same domain basically for the other half of the ellipsoid, discrete ellipsoid, and then we just glue those two domains, as you can see, like this. Then we fold it along this line, and so this point here becomes this point, and this point becomes this point. So what we're basically doing is we're taking two rectangles and glue them along the edges. That's the combinatorics. And so you get topologically, you get a sphere. And those points here, here, and here, those corners are exactly the discrete analogues of the umbilic points. And so I think I have maybe 1 minute or two. So here's a picture. So this is a discrete ellipsoid. The red lines are the discrete lines of curvature. And then I also drew the diagonals. So you can see those green polygons and those yellow polygons. And the question is, well, what are they? What are the properties? Well, it turns out they are actually planar polygons. Those green and yellow polygons are planar, and they lie in parallel planes. And those vertices here are degenerate, degenerate closed polygons. So you can think of those yellow polygons as discrete circles, and also the green ones. And they are in parallel planes, just like in the continuous case. And
sorry, Wolfgang, I think I have to.
Yeah, I'm done. So here's the dual. Here's the dual case, and so here's the theorem. So when you now start deforming, those discrete circular cross sections don't change. They just change their position. So we have exactly the same property as in the continuous case. This deformation property is still preserved by this discretization. And that's really all I wanted to say. Thank you.
Thank you very much for the wonderful talk, Wolfgang. Bao Feng would like to ask a question.
Thank you for very nice talk. And but because of the schedule, I was late. I would like to see the slides and also the half integer. That is very interesting in our recent study for the BKP, CKP reductions. We also see these half integer top functions, and we will look into the connection between your study. The question is, for the Psi-Gordon equation, you have in two coordinate system. One is in the light cone coordinate system, another is in laboratory coordinate system. Yeah. And they just have a rotation of 90 degrees. For the light cone system, we know the fully discrete version and the semi-discrete version. But for the laboratory, recently I learned from Dimitri University that there's no fully discrete or even a semi-discrete integrable discretization. I wanted to know some comments from that. Sorry, it may not directly relate to your.
Well, actually, I wonder whether there's a connection, with mutually diagonal coordinate systems, as you just mentioned. Well, I mean, if you take a pseudospherical surface and you parameterize it in terms of asymptotic coordinates, then the underlying differential equation is the sine-Gordon equation in light cone coordinates, right? And of course, if you then take, if you take those asymptotic coordinates and you scale them appropriately, if you then take plus and minus, so the sum and the difference, you get curvature coordinates. That then the underlying differential equation is your sort of physical sine-Gordon equation. So those surfaces, either asymptotic coordinates are natural, and then we have the usual discretization, a la Bobenko, Pinkal, etc., right? And Hirota, of course. Or you take curvature coordinates on those surfaces, and then you can discretize them. Well, and then this is also known, and you get an integrable discretization. So this is work you can find, for instance, in some of my papers. So at the surface level, you can actually play this game. So you have a discretization, sort of, it encodes a discretization of the sine-Gordon equation, but actually writing it down as a single equation is probably impossible. However, at the surface level, we have two different discretizations of the sine-Gordon equation. It's just encoded in geometry. That's really something that one should look at. So if you formulate, the equation underlying pseudospherical surfaces, not in terms of the sine-Gordon equation, but maybe in terms of the Gauss, the normal or something else, you can actually find discretizations, right? It's just because you're insisting on a special differential equation, form of the differential equation governing those surfaces.
Yeah, thank you very much.
If I may ask a question, there's 1 minute left. I guess the obvious question is higher dimensions. I mean, elliptic coordinates exist in any dimension.
I've just focused on 3 of them. So these discrete confocal coordinate systems, so these discrete orthogonal coordinate systems, they exist in any dimension.
Oh, great. Okay. And then what about degenerations of these coordinate systems?
So this is multidimensional consistent. But it's really an interesting topic because multidimensional consistency of the standard discretization of orthogonal coordinate systems is well known. But since I have this sort of lattice and the dual lattice, it's actually, the question is, what does one actually mean by multidimensional consistence? So introducing another dimension, so you start with, say, the union of Z3 and its dual, and then you want to add a dimension. So it's not quite clear. But if you just start with a Zn and its dual, everything goes through and there's no problem. It has nothing to do with the dimension. I was just focusing on 3 dimensions for obvious reasons. Yeah.
Hello.
Can I just ask a very quick question? You mentioned QRT maps as a natural consequence of the elliptic parametrization. I wondered, how many free parameters do you get? Do you get the most general QRT map?
Well, I get the most general. Yeah, I mean, basically the connection is just the elliptic functions. I mean, I get the elliptic functions are arbitrary, really. So I can choose any elliptic functions here. So I mean, this is a rather vague statement, and I would have to make that. I mean, I would have to spend some time on explaining what the connection is. But there's clearly a connection with QRT maps. But this is, it would just, I just couldn't really talk about this. So there are lots of, integrability connections, and but we're still thinking about whether we can actually develop a complete theory, sort of based on this new notion of discrete orthogonal coordinate systems. So maybe a different way of defining isothermic surfaces, for instance. So that those discrete quadrics actually become discrete isothermic surfaces. At the moment, they are not in the usual sense.
Okay, thank you very much, Wolfgang, again.